Hey guys, what's up? John the Mechanic here. So for 2019, Nissan has totally redesigned their engines that they're putting into Altimas. They now have a variable compression turbo, which is totally redesigned inside and out. And they also kept the naturally aspirated 2.5 liter 4-cylinder, but this one's 80% new, totally new from the bottom up also. So I figured the easiest way to explain it is just to upload the same new model introduction video that I have to watch and all technicians have to watch. So here it is. Hope you guys like it. Leave a comment.
The 2019 Nissan Altima may be equipped with one of two engine choices. The standard engine still displaces 2.5 liters, but the new PR25DD engine is over 80% new for the 2019 model year. When Altima is equipped with all-wheel drive AWD, the PR25DD is the only available engine choice. This module provides an overview of the changes, features, and improvements of the PR25DD engine. The PR25DD engine is more than just a simple revision to the QR25DE engine from the previous generation Altima. The PR25DD is a major redesign of the inline 4-cylinder engine to increase horsepower, torque, and fuel economy while reducing engine noise, vibration, and harshness, NVH, and combustion emissions. The PR25DD was also designed to reduce the mounted height of the engine to allow a lower center of gravity and contribute to the low and wide styling of the new Altima. The PR25DD engine includes a cylinder head design that reverses the orientation of the intake and exhaust when mounted in the engine bay. By moving the exhaust ports to the back of the engine bay, the exhaust manifold, catalyst, and downpipe are packaged to allow a lower engine mounting position without sacrificing ground clearance. The PR25 uses a thermal insulated resin intake insert between the intake manifold and cylinder head. This resin insert creates an air layer to help reduce intake air temperatures into the combustion chambers. Cooler intake air temperatures result in improved power, torque, and fuel economy. The PR25DD implements highly precise electric intake valve timing control, EIVT, and oil pressure-based exhaust valve timing control. The PR25DD engine uses an EGR volume control valve and an EGR cooler system. The ECM uses the EGR volume control valve to regulate the flow of exhaust gas to the intake manifold. The exhaust gas flow rate is controlled by opening or closing the EGR path in the EGR control valve. A built-in DC motor moves the valve continuously corresponding to the ECM output signal. The EGR volume control valve position sensor detects the valve position and sends the voltage signals to the ECM. The water-cooled EGR cooler cools the gas circulated by the EGR system to lower the combustion temperature and improves fuel efficiency by raising the thermal efficiency. The opening angle of the EGR valve varies for optimum engine control. The optimum value stored in the ECM is determined by considering various engine conditions. Refer to the ESM for details on when to perform the EGR closed position learning procedure. The PR25DD engine uses a direct injection gas DIG fuel system to increase power and fuel economy while reducing emissions. The high-pressure fuel pump is located near the top left side of the engine and is driven by a lobe on the exhaust camshaft. The 2019 Altima SR and Platinum models may be equipped with Nissan's first variable compression ratio engine. This new powertrain provides significant benefits in fuel efficiency, emissions reductions, power-to-displacement ratio, and weight savings. This module provides an overview of this new powertrain and introduces the concepts and technologies used in a variable compression ratio engine. Upon completion of this module, you will be able to define compression ratio and understand the benefits of being able to change from lower to higher ratios. Identify the components that are used in the KR20DDET to vary the compression ratio and how they differ from a conventional fixed compression ratio engine. Understand the operation of the variable compression ratio engine. Understand the operation of the new active torque rod. Identify airflow in the turbocharger system and the purpose of the electronic wastegate and compressor bypass valve. Identify the components and operation of the fuel system. And identify the components and operation of the variable valve timing control system. Static compression ratio refers to the relationship of the combustion chamber volume at bottom dead center (BDC) and top dead center (TDC). Higher compression ratios can increase combustion efficiency in normally aspirated engines, especially when direct injection is incorporated. Lower compression ratios are often used in turbocharged applications to allow safe combustion as cylinder pressures increase under boost. In a conventional engine without variable compression ratio, the compression ratio is set based on the bore of the cylinder and the stroke of the piston. In a conventional engine, the piston moves up and down in the cylinder bore because it is attached to the connecting rod that rotates along the crankshaft journal. Because the crankshaft rotates on a fixed axis, the piston stroke will always remain the same. The KR20DDET engine in the 2019 Altima is the first Nissan engine to use variable compression combustion technology. A multi-link system is added to the reciprocating engine assembly that allows the engine's compression ratio to be mechanically varied for a compression ratio of 8.0 to 1 up to 14.0 to 1 by actively changing the upper and lower limits of piston travel within the cylinder. On a variable compression ratio engine, instead of a connecting rod attaching the piston to the crankshaft, an upper link attaches the piston to a lower link, which is connected to the crankshaft. The other end of the lower link is attached to a control link, which connects to the control shaft. A VCR motor drives an actuator link to adjust the fulcrum angle of the control link, which in turn controls the fulcrum angle of the lower link. Because the lower link is also attached to the upper link, when the angle of the lower link changes, the upper link and piston length stroke changes in response. When lower compression is required, the VCR actuator holds the actuator link in the retracted position, and the piston upward travel is limited. Lower compression is desirable during turbocharger boost when maximum power output is desired. When higher compression is required, the VCR actuator extends the actuator link, which changes the geometry of the control link, which rotates the lower link, which changes the effective stroke of the upper link and piston. Higher compression is desirable when trying to maximize fuel economy or reduce emissions during idle, low load, or cruising conditions. In addition to the benefits of variable compression for efficiency and power on demand, the geometric design of the VCR engine also helps reduce friction and cylinder wear due to the reduced side thrust of the piston in the cylinder bore. Using a lower link helps the upper link stay closer to straight vertical during piston stroke. The VCR engine is also more naturally balanced compared to a conventional inline four-cylinder engine that uses balance shafts to reduce vibration. The VCR actuator is a 12-volt, three-phase DC motor that is controlled by the VCR control module. The VCR actuator assembly may be serviced separately if needed. The VCR motor drives the actuator link. The end of the actuator link includes a pin that rides in a retainer and transfers movement to the control shaft and link when the actuator link extends or retracts. This movement changes the angle of the lower link to change the piston stroke. The VCR actuator is controlled by the VCR control module based on signals from the ECM. If the VCR control module or VCR actuator is replaced, VCR base position learning must be performed using a consult work support procedure. Another new powertrain technology used on KR20DDET applications is an active torque rod. The active torque rod is an active engine mount on the upper mounting location. The mount uses a reciprocal actuator motor that isolates and dampens engine vibrations by counterbalancing the vibrations. The active torque rod also includes a G sensor that detects the effectiveness of the vibration reduction and can provide feedback to modify the motor action if necessary. The active torque rod reduces engine noise by approximately 6 decibels. The active torque rod is operated by a dedicated control module based on engine RPM and load information from the ECM. The KR20DDET turbocharged engine receives outside air and filters the air before it flows down into the turbocharger compressor inlet at the back of the engine. Cool air is compressed in the turbocharger compressor and exits upward through the compressor outlet as hot air on its way to the charge air cooler inlet. An intake noise suppressor located at the top of the engine helps reduce intake air noise and resonance. Hot air enters the charge air cooler inlet near the right side of the lower radiator support. The charge air cooler is an air-to-air heat exchanger that uses its large surface area to release heat from the compressed air before it flows to the throttle actuator. The electronic throttle actuator regulates the quantity of air that enters the intake manifold. The throttle actuator assembly includes engine coolant connections for heating and cooling. Air passes through the throttle actuator and into the composite intake manifold. The intake manifold houses the swirl control valve. The swirl control valve creates a swirling effect for incoming air at each combustion chamber during idle and low-speed operation when the valve is in the closed position. Under other conditions, the swirl valve opens and reduces intake air restriction for increased airflow. The KR20DDET uses a single turbocharger that operates when the VCR system is in lower compression positions. The turbocharger is mounted to the integrated cylinder head exhaust manifold and includes oil passages for bearing lubrication and coolant passages for cooling. Combustion gases leave the exhaust manifold and spin the turbine before exiting through the catalyst to the exhaust system. The close proximity of the catalyst results in faster catalyst heating and emissions reductions. The turbocharger system uses an electronically controlled wastegate. The wastegate can be closed quickly to generate boost pressure. The ECM can control the position of the wastegate to regulate boost pressure, prevent overboost conditions, improve fuel economy, warm the catalyst quicker, or conditions when the ECM determines boost pressure is not needed. The ECM performs wastegate actuator positioning calibration during ignition key-on. The turbocharger system also includes an electronically controlled compressor bypass valve. The compressor bypass valve can be opened if the throttle actuator is closed quickly, so pressure does not build upstream of the throttle actuator, and to prevent compressor stalling when the throttle plate is closed quickly. When the compressor bypass valve is opened, air is redirected to the intake side of the compressor wheel to reduce air pressure between the compressor outlet and the throttle actuator. In addition, the ECM monitors turbocharger revolution speed using a turbocharger speed sensor near the compressor side of the turbocharger. The in-tank fuel pump delivers low-pressure fuel to a junction near the inlet of the high-pressure fuel pump. At this junction, low-pressure fuel is supplied to the high-pressure pump inlet and to the low-pressure port injector fuel rail. The KR20DDET engine uses both low-pressure port injectors and high-pressure direct injectors. Direct injection allows for proper fuel atomization under high compression operation and reduces emissions by heating the catalytic converter faster. Multi-port injection optimizes fuel injection while under load. Direct injectors operate under all operating conditions, while multi-port injectors operate under boost conditions. The high-pressure fuel system includes a high-pressure fuel pump that receives fuel from an in-tank fuel pump. The high-pressure fuel pump is driven off the exhaust camshaft and pressurizes the fuel to be sent to the high-pressure fuel rail. The ECM uses the fuel rail pressure sensor to monitor fuel pressure in the rail. The ECM commands the control valve in the high-pressure pump to regulate the fuel pressure in the rail based on fuel delivery needs. Valve timing control is incorporated on both intake and exhaust camshafts. Exhaust valve timing is accomplished hydraulically using engine oil pressure. Intake valve timing is accomplished using a quick and precise electric system. The electric intake valve timing control system operates in a similar fashion to other Nissan vehicles, but the motor is internal to the sprocket rather than external. Click each button for more information on the electric intake valve timing control system. The electric intake valve timing control actuator includes a sensor in the center of the assembly. The sensor includes 3 rings that monitor the position of the 3 outer points, 6 legs, and 6 inner points of the center target. The center target is pressed into the motor armature and rotates at the same speed as the motor. For this reason, if the center target is removed from the motor, it must be replaced. The intake sprocket includes a helix on the back side that fits into the camshaft alignment dowel. Intake motor force moves the helix on the intake sprocket to adjust intake cam position when advance or retard is required. The 3 rings of the sensor monitors the 3 outer points, 6 legs, and 6 inner points of the center target to determine intake motor position and speed. This information is processed by the electric intake valve timing control actuator and is sent to the EIVT control module. The EIVT control module communicates with the ECM to determine camshaft sprocket timing and whether advance or retard is required. The intake timing control motor spins at camshaft speed at all times when no advance or retard are required. When advance is required, the motor is slowed by the required amount to make the helix move the camshaft in the advance direction. After the required advance is achieved, the motor is returned to camshaft speed. When retard is required, the motor speed is increased to make the helix move the camshaft in the retard direction. After the required retard is achieved, the motor is returned to camshaft speed. At engine off, the motor is unpowered and the last rotation of the camshaft, crankshaft, and timing chain manually rotate the helix to the full retard position. Before the engine is started, the helix is moved to the full advance position, 50 degrees plus. As the starter disengages and the engine begins to idle, the motor is energized and the camshaft is positioned to approximately 23 degrees to 24 degrees, neutral position. From the neutral position, the camshaft can be advanced or retarded to meet engine performance requirements.